This part of the tutorial is probably the most difficult one. So far we've seen how we apply post-loss estimation on one single sample. Now I want you to generate 100 different samples and apply the code that we did only on one sample on 100 different samples as well. So this part of the code is the code that generates 100 samples. The general idea is that we say how many observations we want to randomly generate per given sample, how many potential confounders there are, and how many number of simulations you want to make. So how many different random samples you want to draw. Then we create a data frame called simulated 100, which will store our 100 simulated samples. But first we create a matrix. It finishes here. This part is content of the matrix. In our case, it creates 100 times 100 times 100 random normal observations. So this will be a vector. And then we chop this vector to fit a matrix with 100 number of columns and 100 times 100 number of rows. If you cannot visualize it, I'm going to show you just in a second. So once we create this matrix, we convert it to a data frame. Why do we do that? Because we want to create new variables that are dependent on confounders, these potential confounders that we just created. So first we do it as a matrix for out of convenience so that we can quickly generate the random variables, like this huge matrix. Then we convert it into a data frame and then we mutate where D is our treatment, which we know depends on variable 1, 2 and 3, plus some random noise. And our outcome variable, which depends on D, and the treatment effect is 1, but it also depends on some other variables, including the first 3 variables, which are, in this case, confounders, plus some noise. Plus, we also want to create a separate column, which will be a counter for each row in our simulated data frame. And finally, we just rearrange some of the positions of certain columns. We want Y and Z be the first 2 columns, and then everything else to be at the end. So I'm going to go into the detail of this big object here. Feel free to skip if this is completely clear to you. So what I'm going to do, I'm going to copy this code and I will use the following code chunk to basically dissect, open it up and show you what is going on in the middle. So I'm commenting out this part, we don't need it. And in fact, I'm commenting out most of this code too, because we want to do it step by step. And to simplify the exposition, this is just to show you as an example what's going on inside. I just say we have just 2 observations per each sample. We have just 4 columns and 3 simulations. So this is 2 number of observations per each sample. And this one is 4 potential confounders, so meaning columns. And these are how many samples we want to generate. Finally, the matrix. We don't need to assign this matrix to and save it as a certain object. This is just for to give you an example of what's going on. Let me show you. So if I put a matrix, even without that. So what's going on when we do R norm n equals to n multiplied by p multiplied by n sim. It generates a vector of random normal observations with mean 0 and standard deviation of 1 and of the length that is equal to 2 multiplied by 4 multiplied by 3. Now we want to allocate this vector into a matrix. We want this object to be put into a matrix with a number of rows equals to n times n sim, so 6 number of rows and 4 number of columns. Voila! This is what happens. Next step we we convert this into a data frame. Let me see what kind of object it is. Yes, now this is exactly the same thing, but now in a data frame format. And finally, we mutate. Now, this mutate function depends on much more variables. We just generated 4, so I'm going to stop after the 4th one. So we generate column D and column Y, and we also generate the sim number, and then we ask to select Y and D as first columns. And here we are. Actually, I want to select sim number as the first one. As you can see, these 2 rows represent the first sample that we randomly draw. The next 2 rows represent the second random sample. And this one is the third and last random sample. Clearly, we can also see what simulated 100, the one that we use with 100 number of observations and 100 number of potential confounders and 100 number of simulations, how it will look like. It will have 10,000 rows and 103 columns, and here is the head. Finally, we want to move this data frame to slice it up such that we have just 100 rows. Each row corresponds to a single simulation, and within that we store the data, the samples. So right now we have this object which has only 6 rows. If I want to group, if I say group this data frame by the simulation number, and then I ask nest the rest of the data. Look at this. This data frame will be transformed into this new table, meaning that it's also, you can work with it as any other data frame. It has 3 rows because we have simulated 3 random samples, and the samples themselves will be now stored within the new column called data. And to see how we access those columns, those samples that are now stored within this column, we can use this code. So this code, the first part, works with this object simulated 100 nested, which took our big data frame simulated 100 and grouped by simulation number and nested it. Now, how does the nested object look like? It has 100 rows because we have 100 simulations and just 2 columns. One is sim number and another one is data. Now, next, this is how the head of this table looks like. And finally, we can subset data, the sample itself. Let's see what kind of object it is. It says it contains a table data frame which has 102 columns. So the nested data frame has as many rows as a number of simulations, and if we say simulated 100 nested, so to take this object, we select column data, and then we take the very first element of this list, and notice that with lists we work with double square brackets. We ask to show us how it looks like. This object here looks like this. So every single object in here is in itself a data frame. What does it give us? Why do we want to nest data frames within a bigger data frame? This will allow us to apply linear model regressions or any other functions on each of these data frames.